Hello students, welcome to lecture number 17. Now today we will be going to discuss regarding reinforced concrete slab, that what are the various type of slabs, what are the codal provisions regarding the analysis as well as design of slab, and what are the parameters which we have to consider, what are the guidelines, recommendations of different type of slabs which we are going to discuss today. So this is a continuation to the design of RCC structures, that is limit state methodology which we are adopting here, and let us go through details from lecture number 17 onward. So first of all, let us understand what is basically RC slab system and what are the various relevant points which we have to keep in mind while doing the analysis as well as design of the slab. So let us try to understand the definition part, that how we can define a slab. So reinforced concrete slab are large flat plates. So they are just like flat plates, and they are supported on reinforced concrete beams, or either can be supported on walls or columns, by masonry wall, by structural steel beam or column, or by ground. So that means here what we are able to understand, that reinforced concrete slab are just similar to large flat plates, and they can be have a different type of support conditions, and either they will be simply supported or they have a fixed type of support, as well as they may be directly placed on the walls as acting as a simply supported type of slab, or they may be continuous type of slab, that means having more than two supports, having more than one span. So that we are going to discuss today. Slab, as everybody is aware, they are most widely used structure element whose thickness, so main criteria is thickness, whose thickness is considerably smaller than any other dimensions. So here thickness will be also termed as the depth of the slab. So depth of slab or thickness of slab is considerably smaller as compared to its other dimensions. That means two sides of the slab, they will be having two type of spans based on the support conditions, whether the slab is supported on two sides or either it can be supported on four sides. Now they are frequently used as floors and roofs in case of buildings. So floor is a one type of slab and a roof is another type of slab, you can say. So they are termed as slab. Decks in the bridges, they are also come under the definition of the slab. And the top and bottom of tank, if there is any water type of tank, then the base of the tank will also be a slab, as well as top, that is covering of the tank, is also a slab. So slabs can be directly supported on soil, just like staircases, etc. So they can be directly supported by soil, or they can be supported by any type of beam, walls, etc. So whatever we have discussed in first point. So that means supporting system of slab can vary. You can directly place it on the soil, or you can just place it at some height with the help of columns or beams. So either there may be a wall type of construction, so you can place slab directly on two walls. That means there will be that type of slab will be supported by walls. Now what they do, they support and transmit load to the walls. So that means whatever the load coming on the slab, that can be transmitted to the walls, or if they are supported by beams, then load will be transferred to the beams. And sometimes we can say that they can transmit the load directly to the column by flexure, shear, or torsion, which you will be able to understand in the coming lectures. Now another aspect which is a very important aspect of a slab, they have very large volume, and hence the mass of the slab may attract large lateral forces which may be due to earthquake or any type of acceleration forces which can be induced. Slabs may be having different type of shapes as well as support condition as we discussed. So they have different type of slabs based on the shapes. They can be solid slabs, they can be rib type or waffle type of slabs. So our main focus will be on solid type of slab which we are going to discuss in this subject. Now in continuation, depending upon the load carrying behavior, that how slab is taking load and how various type of movements are acting on the slab, they can be classified into two ways. Number one, that is a one-way type of slab, and the second type of slab is two-way slab. So what is the meaning of one-way slab, and what is the meaning of two-way slab, and how they are differentiated? Let us going to discuss now. And the choice of slab for a particular structure will be largely depending upon the economy. That means economies and consideration, uh, and it depends upon buildability, that how easily you can build and what will be the methodology of construction, and loading condition as well as length of the span. So accordingly, we have to decide that what type of slab we can take into practice based on all these parameters. Now, a slab is generally designed as a flexural element, just like a beam. Here, what we have to do, we will be taking a strip of 1 meter width. That means if a slab is suppose having 10-meter long, then we will be designing 1 meter strip of the slab, and that information or reinforcement, whatever we are able to get, that will be uh, carry forward throughout the slab. That means whatever be the reinforcement designed in 1 meter width, that will be taken throughout the slab. So even though it is cast in one piece and not in strips of unit width, but methodology of deciding or designing the slab is by taking 1 meter width. So that means it will be just like a beam having some particular depth as well as having width is equal to 1 meter. So economy of the slabs largely depend upon the thickness, because it any slab may be like this. It may have huge length of the span, and ultimately, if you are taking the depth of the slab, suppose this is just like a slab, so this depth of slab will be directly influencing the volume of the slab. That means how much material is required, and accordingly economy will be uh, checked. So whatever be the cost of the slab and the construction material which we have to require, that directly depend upon the thickness of the slab. So prime factor here in slab is thickness is one of the important factor which we have to take into consideration. Now for design purpose, slab can be taken equivalent to rectangular beam, as I have already explained, that it is just like a, you can design it as a, you have designed a beam, maybe just like a singly reinforced type of beam. So we can design it as a rectangular beam, but what here changes is the width. Generally in case of beam we take 300 or 350 like that millimeter, but here we are taking the width of the that particular strip as 1 meter. So it can be just it is just like a rectangular type of beam having width is equal to 1000 millimeter 1 meter, and whatever be the depth. So it will be just like a rectangular beam. Now as slabs we are going to discuss, the slabs are thin compared to the beams, having depth comparatively lesser as it is comparatively lesser as compared to the depth of the beam, you may have designed various type of beam, and their width generally varies from 400 for 450, 500, 550 like that. But in case of slabs, you will be finding that most of the slabs are having the depth range, sorry, thickness range from 150 mm to 200 or 220 mm, just like that. So the serviceability limit state of deflection is normally critical in these type of slabs, and rather than ultimate limit state of bending and shear. So a very important aspect of the slab design is serviceability, which we have to take into consideration carefully. Now slabs, due to relatively larger surface area as we discussed compared to their volume, are more affected by temperature, because you know that whatever be the effect of temperature, that directly get influenced by how much surface area is exposed to the weather conditions. So in case of slab, whatever be the volume of the slab, but you will be observing that surface area will be comparatively higher. So if surface area is more, then definitely temperature effect will be more, and ultimately it will be going to develop shrinkage stresses, and secondary reinforcement is required to resist these stresses. So later on we will be going to discuss what is the meaning of this secondary reinforcement. So shear stresses, if we talk, they are not such critical in case of slab, but in beams they are more critical. Now RCC slab, as we have discussed already, they may be categorized into two categories based on the way how they support the load on it. Now, very first type of slab which we later on we will be going to design, that is one-way slab, and another type of slab which is two-way slab. Now, first of all, let us understand what is the meaning of one-way slab, how it behave, and what will be the behavior with respect to the loads and movements in case of if the slab is to be designed as a one-way slab. So, one-way slab are those slabs which carries load on their shorter span. So you are well aware that if we are taking a slab, then it will be having two dimensions, so two spans we can say. One will be the longer span, other will be the shorter span. So when the load is directly carried by shorter span, then that type of slab is known as one-way slab. Now you can see from this diagram, here there is a support, one support, and another support, just like two brick walls. And when slab is placed on these supports, then you will see that it will be having a bending shape like this. So that means whatever the load, that load will be transferred uh, along the shorter span, and from this side it will be transferred on the shorter span. So longer span is free. So that means you will be able to understand that whatever be the deflection or bending due to the loads, that will be uh, predominantly greater along the longer side of the slab or longer span. So that's why we have mentioned here that one-way slab carries load on their shorter span. Now ratio of the longer span to shorter span, here we have to take into consideration. So here, if the ratio of span along the longer side, that means length of the longer span divided by length of the shorter span, is greater than or equal to 2. That means Ly is greater than Lx, where Lx is the shorter span, and on which the slab is supported, as we have discussed, which is required to transfer the load. And then this type of slab which is having ratio Ly by Lx greater than or equal to 2, that type of slab is known as one-way slab. Now bending, if we take bending, the bending will be along one direction, particularly perpendicular to the direction of the supported edge. Now these are the supported edge, and this direction is the perpendicular direction to the support edge. So bending will be predominantly along this direction. So that means what we want to say here, that if you are just placing a slab which is supported on two sides along its shorter side, then its behavior as we can see in this diagram, then this beam, this slab we have to design as a one-way slab. And you can easily understand that where we have to place the reinforcement so that this deflection can be removed. Now this will be the sectional diagram of the slab. It is a simply supported type of slab. You can see the both end they are having any brick wall type of support, and this rectangular portion is a slab, that is a one-way slab particularly. So this one-way slab, it is a simply supported type of slab. You can see there is a blue color line. It indicates the main reinforcement. So that means here you are supporting the slab, here you are supporting. So when you are providing reinforcement in this direction, so that reinforcement is basically the main steel or tension steel, we can say. So that means we have to design the steel along this direction. But as we have discussed earlier, that we have to provide distribution steel also. So distribution steel will be in the direction perpendicular. So this will be the direction in which we are providing the distribution steel. So one thing you have to take into consideration, that in case of one-way slab, we have to design the main reinforcement, but distribution steel is not required to take any bending stresses, but it is provided to take temperature type of stresses. So sometimes this distribution steel is also known as temperature steel. So you have to provide minimum steel as per IS 456. So that will be minimum steel will be termed as a distribution steel. So as we have discussed, main steel is provided along or parallel to the direction of span, that is between the supports. And the distribution steel is provided in a direction perpendicular to the main reinforcement. So again, if we go through this diagram, and then these black color bars which you are able to see, these are the distribution steel, and blue color bar, it is a main reinforcement which has to carry all the bending moment. Now let us discuss what is a two-way type of slab. So two-way type of slabs are those slabs which is supported on all of the four sides, but load is carried on and the load is carried on the both the spans. Yes, so that means slab which is supported on all the four sides and the load is distributed on all the spans. The ratio of longer span to shorter span here, Ly by Lx is less than 2. Again, where Lx is the shorter span and Ly is the longer span. Now, when this type of slab, you can see in this diagram, these are almost they are having equal span length, almost equal span length. So that means their ratio of one span to another span, that is Ly upon Lx, may be less than 2. So what you will observe, that since the slab is supported on all the four sides, so when load is coming on the slab, then slab the bending behavior will be similar to this diagram as here we can see. That means you have to provide reinforcement in both the directions. Now here we will be providing main steel in both the directions. That means this is main steel along one direction and this is also main steel on the other side. So no distribution steel is need to be designed, because you can see that bending is, if I say this is x direction or this is y direction, then bending is very much effective in both the cases. That means this load will give you a bending of the slab in both the direction. So we have to provide steel along the both the directions. As I discussed, that bending exists in both directions, and you can see here that here blue color as well as black colors, the steel, both steel are termed as main reinforcement, that is tension reinforcement. So we can say tension reinforcement along x direction as well as along y direction, or better to say that tension reinforcement along longer span as well as shorter span. So to resist these movements, the slab must be reinforced in both directions by two layers of reinforcement and that are perpendicular to each other, which you can see in this diagram. Now let us discuss what are the various design steps which we have to follow when we have to design RCC slab with the limit state method, and which is a simply supported one-way slab. So we are talking about the one-way slab which is simply supported. So what are the various design steps as per IS 456, and that we are going to discuss now. So you have to listen carefully. So again, as we have discussed in various design of a beam type of element, that means singly reinforced beam and doubly reinforced beam. Now design methodology is just similar to beam design also, and in step number 1 we will be just going through the grade of material. So here again we can assume a grade of a concrete based on the environmental conditions, as well as steel if they are not provided in the design. If they are provided, if suppose a grade of concrete and grade of steel is mentioned in the numerical problem, the design problem, then you have to follow the same value. Otherwise you have to check the statement, that means what information is available regarding the exposure condition. So based on exposure condition and with the help of IS 456, you have to pick the value which is more relevant in case of grade of concrete as well as steel. So again, we are always more concerned about the recommendations of IS 456. Now in step number 2, we have to evaluate what should be the effective span of the slab. So here you can refer clause number 22.2. Again, same clause which we have referred in case of design of beam. So first of all, let us discuss how to assume or how to take the width of the slab. So for design calculation, as I have already discussed, width of the slab is taken as 1000 millimeter. That means 1 meter width will be taken. So that means what we are going to design, when you have to design the slab, then you have to take a strip for the design, and that strip of slab having width 1 meter. Now next step is the effective span of slab. How to get the effective span? So you can see here there is a slab, and that slab is supported on the two walls. So that means it is a simply supported type of slab and having clear span length LC and center to center support distance. This will be the center to center support distance. Now if it is a simply supported slab, as you can see in this diagram, then slabs that are not built integrally with the support. That's why we are saying that it is a simply supported slab. So such type of slabs supported on generally on brick walls. So very first condition is effective span length is equal to LC plus LD. LC you can see here, it is the clear distance or clear span length between the face of the two supports. And D will be the effective depth or thickness of the slab which we are going to design. Then second is center to center support, and again we have to take whichever is the lesser value, and as we discussed, LC is the clear span between the support and D is the effective depth of the span. So this formula or this condition is valid when it is a simply supported type of slab. Now if it is a continuous type of slab having more than one span, just like this, so there may be having number of spans. They may have a equal span length or they may have different type of span length, as well as width of support we can say it is BW. So this type of slab which we are going to design, first of all, since this slab is ending at this support, so we will term it as end span. So that means this particular span is end span. If I take that this is the end span, and the other span will be the interior span or intermediate span, depending upon how many spans are there. So first case, as already given in the IS 456, if the width of support is less than LC by 12, then effective span length is equal to LC plus D, or center to center of the supports, whichever is lesser. Now case number 2, if the width of support VW is greater than LC by 12 or 600 mm, whichever is less, then we can say for end span. Now you can see this is end span. If you are going to discuss this span, that means you are going to design this span of the slab, where one end is it may be fixed and other end may be continuous. Here, if one end is fixed, now earlier we have discussed simply supported. Now it is a continuous type of slab. Here there may be a fixed type of support also. So both the possibilities are there. If it is not a fixed type of support, then first condition will be easily applicable. And for end span with one end fixed and other continuous, or intermediate span, then L effective will be equal to length of the clear span. And for end span with one end free and other end continuous, now if this is the first case, if this end is not fixed, that means this end is free, simply supported, and other end is continuous. So this will be the continuous end, this will be the free end in case of if it is placed on the walls. So then you have to take note of this particular step number 2, and accordingly we have to find out what is the effective length of the span. And the third one again, which we have already discussed in case of beams also, span with the roller or rocker bearing, then L effective will be distance between the center of the bearing. So by this step we will be able to work out what will be the effective span of the slab based on the various type of end conditions and based on the width of the support. Now step number 3 here, sometimes we call it as thickness of slab, or you can say depth of the slab. Here you can refer the guideline given in clause number 24. So thickness of slab can be decided based on the deflection requirement. We have already discussed in the previous slides, similar to that which were considered in the design of beams. So again we are repeating that because we are taking 1 meter width of the slab for consideration. So many things of the design or parameter of design are similar to design of a beam. So very first is checking the actual deflection against the allowable limits, and the second is based on the maximum span to depth ratio specified for serviceability criteria, which can be assumed to not exceeding span by 250. So this information is available in this clause number 24, from where you can go through the guideline carefully. The overall thickness of slab, how to calculate? So it is very simple. Again the same formula in case of beam which we are going to discuss now. Total depth of the slab is equal to effective depth of the slab plus clear cover, which is we have to decide as per IS code requirement, then half the bar diameter of the main reinforcement. Now you can see here one difference is there. In case of beam, we were taking in this calculation of the total depth of the beam, there was a diameter, one diameter of the stirrup was considered. But here in case of slab, we are not providing any stirrup type of shear steps. Shear steps are not provided. So directly you can use this formula to work out the overall depth of the slab. Now what you have to consider that main reinforcement is provided along the shorter span, and it is provided at the bottom, and distribution steel is provided above the main reinforcement. Now clear cover. Some clear cover is required, so clear cover required to be provided to the reinforcement. We can refer guideline mentioned in clause 26.4. And another very important information is diameter of the steel bar. So what is the codal provision regarding the diameter of the steel bar which we can use in slab? It should not be greater than 1/8 the thickness of total thickness of the slab. And for guideline you can refer this clause. So what is the size of the diameter of the steel bar which we can consider. So upper limit is given, it should not be greater than 1/8 of the total thickness of the slab. So this check you can apply before just assuming or selecting the diameter of the main steel. Now step number 4, how to calculate loads and bending moments. So let us discuss. This is again we are talking about the particularly one-way type of slab design. So we are again considering 1 meter or 1000 millimeter wide strip of the slab for loading calculation. So this is the way that you can see here we have selected this strip which is having width 1 meter. So this strip we will be going to design, and ultimately whatever be the reinforcement etc. we will work out. So same will be provided throughout the slab. First of all we have to calculate self weight of slab. Now per meter length. This is per meter length. So that means whatever we are going to do the calculation, bending moment etc. or design of the reinforcement. So everything is done for particularly this strip of 1000 millimeter. So you can just consider that you are going to design a beam having width 1000 millimeter, and you can assume that this slab is made up of such type of a number of beams having width 1000 millimeter, but depth will be equal to the depth of the slab. So self weight of slab per meter length we can easily calculate. That will be the dead load to be calculated based on the assumed dimension which we are going to assume, and based on the unit weight of concrete. So that means overall depth whatever we are able to work out, and width will be 1 meter. So this will be in the units of kilonewton per meter square, because this is 1 meter and we are taking always 1 meter length of the for the consideration of the load, because you calculate self weight per meter length and another is 1 meter width. So that's why we have taken kilonewton per meter square. So since slab carries load of surface finishes, so definitely in case of beam, many of time we need not to provide any surface finishes, but in case slab you have to provide surface finishes, because it is slab is considered as a roof or a roof or floor. So that means floor finishes we have to provide, either maybe in the form of tiles or maybe any other type of it as per your requirement. So what we have to do, we have to a suitable value of finishing load can be assumed, and that will be also added to self weight of the beam. So that means total uh, dead load of the slab, you can say total dead load of the slab will be self weight of the slab per meter length plus whatever be the floor finishes load. Now live load on the slab, WLL, we can take it as WLL live load. It will be also taken as a UDL, but because we are taking strip is equal to 1 meters, so it will be in the unit of a kilonewton per meter square. So both the loads, whether it is a dead load of the slab or whether it is live load on the slab, they will be having the same unit, kilonewton per meter. So here you have to take care during the calculations. So mostly this live load is provided in the design problem. If it is not provided, then just like we have done in case of a beam design, you have to take the help of IS 875. So total factored load we will be calculating. So first of all we will be adding both the loads. So total load per meters length we are able to calculate, that is W dead load plus W live load, and then partial safety factor we have taken 1.5 for dead load and live load. So total factor load capital WU, it is for ultimate, so that will be calculated in the by using this formula, and this total factor load will be in kilonewton per meter square. Now next step is bending moment and shear force calculations. So factored bending moment can be calculated as per the support conditions for one-way slab by using formula which we have already developed in structure analysis. when we are using the load as a uniformly distributed load. So various type of formula which you can just get from any standard book of structure analysis. That means if it is a simply supported slab, then the maximum bending moment, we are aware that maximum bending moment will be at the middle of the span. So formula you can use WL square by 8, and similarly maximum shear force you can calculate. And if it is a fixed end type of slab, then this will be the formula, both the formula for maximum bending moment and the maximum shear force calculation. And if it is a cantilever type of slab, then again you have to use the same methodology which you have gone through and studied in structure analysis. So based on those information, you are able to get this value. So this will be the factored bending moment, maximum factored bending moment, because while calculating W, we have already taken partial safety factor. So here we will not be using any partial safety factor. Whatever be the value you are getting from this table, so that will be maximum factored bending moment, which we have to, for which we have to design the slab. Now step number 6, here we have to check whether the depth which we have provided, that is adequate. So now the depth of slab adopted earlier need to be checked for adequacy, so that whether it is able to resist bending moment or not. Whatever the bending moment, that is factored bending moment, for which we are going to design the slab. And here again we are considering the section as a balanced type of section. So required depth of slab, that is D, capital D required, we can calculate again from the same equation, that is mu is equal to 0.138 FCK BD square. This equation, as you remember, this equation is valid for a balanced type of a section. And but only thing changes here, that width you have to take, that is equal to 1000 millimeter, because again I am reminding you that what we are going to design, we are designing the slab in the form of steps. Now step number 7, what should be the area of main reinforcement and distribution steel? So main steel, which we are calling it as a tension steel, that is AST. How to calculate? So area of reinforcement which is required to resist the ultimate bending moment can be calculated by using the same equation of singly reinforced section. So mu you can get this formula from an Engg G of IS 456. So based on this formula, you have to take the limiting value of movement is equal to ultimate movement, that is factored bending moment, and Fy you know, because it is the yield strength of the steel which you are going to use. AST which you have to work out, that you have to calculate from this equation, and V is the width of the strip, that is 1 meter. Small d is the effective depth of the beam slab, and FCK you know that characteristic compressive strength of the concrete which you are using. So by putting the available information in this equation, we are able to get what is the AST required. So area of tension steel required can be worked out with the help of above mentioned equation as already discussed, and accordingly steel bars of suitable diameter arranged in the slab throughout the span at a suitable spacing. Now here, in case of a beam, what we were doing, we were adopting a particular or any assuming a diameter of a bar, and later on we will be working out how many number of bars are required. But in case of slab, we are not calculating number of bars, but we will be deciding or arranging steel by taking the spacing into picture. That means how much center to center spacing of the reinforcement bars are going. So here we have to decide the spacing. In case of beam, we were deciding the number of bars. So one note, the above area of steel is calculated for 1000 millimeter of width of strip, and so similar steel is extended throughout the span of the slab. Now required spacing between parallel bars. As I have told that our focus is on the spacing. So let us first of all check how much spacing is required, and that is particularly for that strip which is having width 1000 millimeter. So required spacing, that is S required, you can get from this formula 1000 into, that is area of 1 bar. 1000 is the width of the strip, area of 1 bar divided by area of steel which is required, which you have already calculated in this step. So that means you have to provide this much area of steel, and this will be the area of 1 bar which you have assumed. And accordingly, using this equation, you will be able to work out that how much spacing is required between two parallel bars which you are going to uh, use in as a tension reinforcement in that strip. Now, the main steel is provided as per required spacing. After checking, here you have to apply another check. That check is specified in IS-45, that is limit of area and spacing limit. So here two type of checks we have to apply. That means what is the minimum or maximum type of steel area required as well as the spacing limit. So you can refer the clause number 26.5.2 for limits related to the area of steel, and 26.3 related to limits which are specified based on the IS code regarding the spacing between the bars. So two information you have to check here. Now, what is the distribution steel? How to calculate distribution steel? As I have already told you that it will be the minimum steel required as per IS code. So you can refer this clause 26.5.2.1. A minimum amount of steel is provided in the transverse direction to the main reinforcement to take care of temperature as well as shrinkage effect in this direction. So that means what is distribution steel? Distribution steel is equal to the minimum amount of steel as per IS 456. So this transverse steel is called distribution steel, or also termed as secondary reinforcement. So if you uh, say that main reinforcement is primary reinforcement, then distribution steel will be secondary reinforcement. And it also help in distributing the load as per clause 26.5.2.1. So beyond this, after 26.5.2.1 and another subclauses, you can refer in case of distribution reinforcement. So if you are using mild steel bars, then what should be the minimum area of steel required? So as per IS code, mild steel reinforcement in either direction in slab shall not be less than 0.15% of the total cross section area. So this is the minimum steel which you need to provide, that is 0.15% of the total cross section area of the slab section. And however, you can reduce if you are taking steel, high strength steel instead of mild steel. So that means if you are taking mild steel, then you need to provide higher steel, minimum 0.15%. But if you are taking high strength deformed bar, then only 0.12% of steel is sufficient, which you can provide as a distribution steel. So, according to this information which we have discussed so far, that means if there is a mild steel bar you are going to provide, then you can work out the how much distribution steel is required, 0.15%. Or if you are providing the high strength steel, then by using this formula you can work out how much is the ACST steel which is required as a distribution steel. So similar to tension reinforcement, spacing again need to be designed for the distribution steel. You have to work out what should be the minimum spacing required. And from this diagram, everything is clear. Now this is a section taken from the slab. You can see this black color bar which you can see, that is the main reinforcement, that is primary reinforcement, and a blue color dark circle which indicates that the steel which is provided in a perpendicular direction to the main reinforcement, and that we call as a secondary reinforcement or distribution steel. And when you are taking the effective depth, then effective depth will be the exactly from the center of the main steel. and the overall depth will be capital T. That is, this is the overall depth of the slab. And what I was talking about the spacing, so this will be the center to center spacing of the distribution steel, which we can show here. Now step number 8, here we have to apply the check for shear stresses at critical section, and you can refer clause number 40 here. What we have to do, we have to apply the check for shear stress at critical section as mentioned in IS 456. So what is the critical section? It is at a distance equal to effective depth from the face of the support, and accordingly we can calculate what is the nominal shear stress that is given by the formula already we have used in case of design of beams. But here again you have to take width equal to 1000 millimeter. So accordingly you can work out what will be the value of the tau v, that is the nominal shear stress. And then what we have to do, we have to apply the check as per table number 19. That means you have to work out what is the value of tau c from table number 19, and then we have to multiply it by factor k, and for this you can refer clause 40.2.1.1. And what are the checks which we have to apply and how to adopt the information. Now if first of all we have to check whether tau v is less than tau c. If this case is the true, then what we have to do, we have to provide minimum shear reinforcement, we have to provide as per clause 40.3. Now second condition is if your tau v, that means shear stress, nominal shear stress is exceeding half the maximum shear stress. What is maximum shear stress? That is tau c max, and tau c max you can get from table number 20. And what code is suggesting that you have to apply this check that whether tau v is greater than half of the tau c max. If this check is okay, then you have to redesign the section. And the third condition is that means if tau v is greater than tau c, and but it is less than 0.5 tau c max. So tau c is the value which you are getting from table number 19, and tau c max is the value which you got from table number 20. So if your slab which you are going to design, it fulfills this third condition, then what you have to do, you have to design the shear reinforcement as per clause 40.4. But one thing you have to note down that in general, one-way slab are not critical in case of shear check. So we have gone through different conditions as per IS 456. That means whichever the condition is true, accordingly you have to design. Either you have to design minimum shear reinforcement, or you have to redesign if second condition is fulfilled. If third condition is fulfilled, then you have to design the shear reinforcement. That means not minimum, but you have to design the shear reinforcement as per clause 40.4. So as already I have pointed out that in case of one-way slab, generally they are not critical in shear, because when we are using this formula Vg by Vd, here V is 1000, which is sufficiently greater. So ultimately tau V value is supposed to be very lesser value. So maybe the first check is okay, that minimum shear reinforcement is required. Now step number 9, we have to apply the check for deflection as per clause number 23.2.1. So check for deflection is to be applied as mentioned in information or guideline in clause number 23.2.1 of IS 456. Now very important point which we have to keep in mind. Now you are well aware that if you draw the bending moment diagram of a simply supported slab, then you will be finding that it will be a parabolic type of shape, and maximum bending moment will be at the middle of the span, and after that it will be decreasing and becoming zero at the simple support. So that's why we have mentioned here, since the tensile steel which you have to design, it is for the maximum value. That means whatever the steel you have worked out, that is for the maximum value of the bending moment. But maximum value of bending moment is only at the mid span of the slab. So if I draw that, if this is a simply supported slab, and if I draw the bending moment diagram, then bending moment diagram will be somewhat like this. That means if this is the support, this is the support, you see that bending moment here 0, bending moment here, bending moment here is maximum. So that means we can say that whatever the steel we are going to calculate for maximum bending moment, that is not required at every section of the slab. So either we are providing more steel. So that's why I have directly mentioned 2 points. The tensile steel need to be designed for maximum value bending moment, and which is supposed to be at the middle of the span, and subsequently it decreases toward the simple support end, and bending moment is 0 at the simple support. So one thing is very much clear, that reinforcement need to be at the middle. Maximum reinforcement is required at the middle of the slab, but at the support end, since the moment is 0, so no reinforcement is required. So what we can do for this, in reference to this discussion, tension steel is not required at support, but still we have to provide minimum steel. So minimum steel is always required to be provided in case of slab, whether bending moment is 0 or not. So what we do in general, it is a general practice that because we are more concerned about economy also. So what we can do, we can decrease the area of tension steel near supports. So near support section we can decrease the steel as per IS codal provision, and that methodology is known as bent up bars. That means you can bend up the bar, so you will be able to understand it later on. Now you can see here the diagram. Let me remove this. So you can see here what is shown here. This slab is supported on the two walls. That means it is simply supported. And below, black color bar is the main reinforcement, and blue color dots are showing distribution steel because it is in a perpendicular direction. Now you can see here, main reinforcement is just bent up at some angle upward. Maybe it is 45-degree angle. So this is bent up and then it is extended at the top level. Because when you are talking about the slab, any type of support, whether it is a continuous support or simple support, then since their movement is 0, but there may exist some negative movement. So what we are doing, we are just curtailing, not curtailing particularly, what we are doing, we are just lifting the reinforcement, main reinforcement, and now we are not providing some part of the main reinforcement which is beyond this point. You can say from the distance from the face of support, that is equal to 0.1 L, we are lifting the bar. So 50% bars we are lifting upwards, and we are providing. These are the alternate bent bars. That means if you have to provide 50 number of bars, then every alternate bar you can just lift, and in the form of bent up bar. So these are the bent bars. So what we are doing, we have reduced the reinforcement area at support section 50%, and the rest of the 50% area we have provided at the top. Now alternate bars are bent up and they are extended to the top of the support, which also strengthen the shear stress capacity of the slab or beam. We can provide in slabs as well as beams at support section. So where shear force is maximum. So that means it will be uh, taking care of the shear stresses also, because you are well aware we are providing in case of beam shear stirrups. So again, this portion of the steel will be taking care of the shear stresses also. So that means we have two advantages. One advantage by providing vent bar, that means where steel is not required, we are not providing there. And but the steel which we are lifting up, that will be taking care of additional stresses, that is shear stresses. So you can see this actual diagram of any site. You can see this one bar is going through the whole span, and this is the third bar, and the second bar we have lifted upward. Then another bar, then one bar is down and another bar. So every alternate bar we are doing, we are lifting it, and that means we are saying that every alternate bar is bent up, and or you can say bent up bars are provided. So bars are bent up at a distance, already told you that at a distance 0.1 L. This information is available in code. So that means you can lift the every alternate bar you can lift at 10% of 0.1 L of the L will be the clear span between two supports. So this information here, one thing is very important, that what we are doing, we are providing 50% of steel at support level. Now check for a development length. Clause number 26.2.1. So as per codal information, development length required can be calculated by this formula, which we have already used in case of a beam section. So where phi is the nominal diameter of the bar, sigma s is the stress in bar at the section considered a design load, tau bt is the design bond stress. You can get the value from the table. Now, what is the development length? Now, development length, as code suggests, that it also includes anchorage value of hooks in tension reinforcement. That means whether you are providing some hooks, so that will be also considered in development length. Now, apply the check. First of all, what we have to do, we have to check whether embedment length of reinforcement bar into support. So how much length of the steel bar which we can take into the support, that is known as embedment length. Now see in this diagram, this was the bent bar. So at distance 0.1 L we have lifted the bent bar. Now this bent bar or main reinforcement, now this main reinforcement, 50% of main reinforcement is going directly into the support. So up to how much maximum distance we can take up to some, that means we have the maximum distance we can take up to the clear cover. So this will be the clear cover beyond which you can't go. So we have to provide the minimum clear cover. So LE is the embedment length of the reinforcement. That means you can, if you want to place the reinforcement in a state form, that means directly, so maximum distance up to which you can take steel into the support section, that is LE, and that means you can easily calculate what is the value of LE. So it will be width of support minus clear cover. Now as per IS 456, condition is given that this embedment length should be greater than LD by 3, LD which you have already calculated. So another condition is LD, that is the development length, should be less than 1.3 M1B plus L naught. Now if you remember what was M1, M1 was the based on the area of steel which you have taken into the support. But here what we are doing, we are taking only 50% bars in tension side. So 50% bar, that means accordingly your M1 will become equal to half of this value, that means 0.5 M. So that means you have to replace M1 by 0.5 M1, and you have to check whether this condition is satisfied or not. Now last step is the reinforcement detailing which we have to do. So simply supported one way RCC slab. So now you can see here more detail. So this this will be the capital D, the overall depth of the slab, and small d, the effective depth of the slab, that means from the center of the reinforcement. These black color bottom bars are main reinforcement. We have already mentioned this is main reinforcement, and every alternate bar is lift up, or you can say bent up at a distance 0.1 L from the face of the support, and you can provide in such a direction. And these are the minimum steel here you can provide to just uh, hanger them these bars so that they can be kept in place. And the main reinforcement, now blue color bars, they are the distribution steel which you are going to provide. So this is the complete design steps, we can say design steps which you have to follow when you are going to design a slab which is one way type of slab. So thank you. Later on we will be going to take some more design problem.